Hi everyone. So thanks very much, Alison. Really enjoying the conference. I'm going to talk about energy storage, but I'm going to talk about storing a different kind of energy. I'm not going to talk about storing heat. I'm going to talk about storing electricity. And the honest reason for that is that that's where we got our funding from. Like this photograph on the left-hand side here, because it shows something that really winds up anti-wind turbine protesters, which is some wind turbines that are moving and some wind turbines that are still. And the reason that happens is that the energy companies have to turn the wind turbines off periodically in order to keep the grid stable. And that results in what are so-called wind curtailments. And the rationale for the work I'm presenting here is the idea that we might be able to use that curtailed wind on windy days when we're producing or capable of producing more energy than the grid actually needs to supply the demand, to heat up water in mines. So this is an EPSRC funded project that started last year. There's a cast of thousands here on the delivery team at the University of Strathclyde in Edinburgh, and a raft of project partners. But this is really just getting off the ground, or under the ground if you like. So the rationale, the UK government has done a bunch of work on how much storage we need. The International Energy Agency similar, but the Energy Network Operator in the UK says we need 40 gigawatts of energy storage by 2050. In the UK, the wind curtailment payments in 2020 added a cost onto your electricity bills if you live in the UK, equivalent to £4 per megawatt hour. And given that the current electricity prices are about £60 per megawatt hour, that's quite a big chunk of extra cost to pay people to turn the turbines off. And that could power 1.25 million homes. So that's the sort of first framing question. The second is that we know decarbonising heat is complex. Recent government report here on the right hand side. I'm not going to go through all of the numbers at the top because you know all of this. But again, just to put the two problems into context, East Ayrshire, which is the part of Scotland that has the highest curtailment payments, £12 million a year, that's equivalent to 120 gigawatt hours of electricity, which is actually really quite close to East Ayrshire's regional annual heat demand of 188 gigawatt hours. Now, East Ayrshire is unusual, partly because it's got a lot of wind farms. It's relatively high up, but it's also relatively rural. So there's only 26,000 people, but there is industrial demand. And obviously we're going to see more wind turbines rolling out in the future. And then finally, thermal energy storage in water requires high volume. So on the left-hand side here, we've got the basement of the first building in New York to achieve a particular certification for greenness. I can't remember what it is, but there are big tanks of water in that basement. In the centre here, we have an image from the GigaWatt webpage, and GigaWatt is a company that suggests they can build you a thermal storage tank. There's a tiny person in the middle here for scale, to give you a sense of the scale of what they're proposing. They're proposing to take water up to 90 degrees in these tanks, but that construction is going to require the disposal of significant amounts of waste from the constructing of the whole. And there are other projects looking at using mines. There's a page from just a few days ago on the BBC looking at using old mines in Sweden to fill those with water to use those as thermal energy stores. And again, for context, a 600 metre deep, 6.5 metre wide shaft, which is about 20,000 cubic metres, could store over 1,000 megawatt hours thermal energy. And those numbers become relevant later, but just to reflect back on Dan Whittington's talk yesterday, that's about the size of the shaft that he's looking at, or about twice the size. I think it was 10,000, 12,000 I think Dan's was. And that's enough heat to heat 1,600 homes in a worst case weather week. And this idea of a worst case weather week is used a lot in energy systems research. So that's one of these beautiful high pressure days in the middle of winter where there's lots of sunshine but no wind, and everybody needs to turn the heating on because it's so cold. So what are we going to try and do? We want to ask the question, can we use mine shafts to store electrical energy as heat? So eliminating the need to get rid of all of this waste material by digging new shafts. And we have a site where we're going to be demonstrating this. This time next year, we should be starting to, or this time next year actually, we should be partway through an experimental program to inject heat. But in order to demonstrate this is a good idea, we need to answer a few questions. So what's the opportunity in the UK? I know one of the first questions anyone will ask is, well, what about most of the shafts are backfilled? So, well, how many of the shafts are backfilled? How many of the shafts are what depth and so on? What about the structural stability of the shaft? So if you cycle temperature up and down, Fiona's beautifully shown that that can affect the rock mass, but what about the structural stability of the shaft material itself, the shaft lining? Will it result in movement or chemistry from happening? Will it result in movement of contaminants? What happens if we introduce oxygen and so on? What happens to the heat as it bleeds out into the surroundings? That was another question this morning, I think, for the geobattery people. And the team at Edinburgh University are calling this heat accountancy. So where is the heat going? But really importantly, how do we plug this into the grid? How do we integrate this system with the wider energy system? And these are linked, these questions are linked. I'll come on to that in a little bit. So what's the mine shaft thermal energy opportunity in the UK? The postdoc working on this is Stephanie Flood. And this is actually work from a previous postdoc, Isabella Ottalega, who kindly was given a database of mine shafts in Scotland from the Coal Authority, and she's plotted up here mine shafts by depth. So the left-hand graph is all the mine shafts at 200 metres or deeper, right-hand is at 500 metres or deeper, and they are situated within the mine blocks, which are the Coal Authority's hydrogeologically connected mine blocks, which are colour-coded by temperature from Gareth Farr's dataset. So you can see there's a large number of holes which are lined, and the deeper ones tend to be the more modern shafts, which tend to be more concrete lined, whereas the shallower ones tend to be the older shafts, which were brick or wood lined, in some cases unlined, which are much less likely to be suitable. And if you look at the population across Scotland, and that's simply because that's the data that Isabella had, and we will be doing this for the UK, you can see the frequency of different mine shaft depths, and you can see the frequency of different mine shaft volumes. And the largest volume mine shaft in Scotland is 40,000 cubic metres. Now, there are 177,000 known mine shaft entries in the UK, but what we don't know yet, because Steph hasn't done the work, is what percentage of those are shafts versus adits. But if only 1% of those were actually usable for this, and they had that volume, that around 20,000 volume, that's equivalent to a worst case weather week demand for 10% of UK homes. So huge numbers of assumptions in there, but there's also a huge potential for this technology. The second question around shaft stability, this is the work of Hua-Chen Yang Chan from University of Strathclyde and his supervisor Shangtong Yang. And Hua-Chen has already started modelling some very basic models of shaft lining and looking at what happens to the radial and tangential stresses as the water levels might go up and down in the shaft. Now, we're not looking at water levels going up and down, we're looking at temperature levels going up and down. But this stage is to look at what happens as those shafts refill. So what's the sort of baseline stresses as those shafts refill? I don't have any data on the chemistry part of the project because we've had some personnel changes. We'll shortly be advertising, just to let anybody know who's finishing their PhD. We'll be shortly advertising for a geochemistry focused postdoc on this project. So the heat accountancy part of the project is Jessica Dassow at Edinburgh. And here again are some kind of her sort of baseline setup models looking at heat conduction in the rock mass around that shaft over, in this case, 100 days. So this is really very preliminary work. Jessica's sort of setting up the model and checking that it runs and thinking about the relevant dimensions. And all of this modelling work is focused on our site, which I don't want to tell you the site just yet because we're still in negotiations with landowners and neighbours. And the final part is integrating mine shaft thermal storage into the energy system. And this is a very busy figure from a previous paper. This is work of Win Eng Yu and Graham Flett, who are two postdocs working for Paul Toohey in the Energy Systems Research Unit at Strathclyde University. The key point here is if we can get the shaft's water safely up to above 55 degrees C, then on those cold weather days, we can plug the water straight into a district heat network without using a heat pump. And what that does from a grid stability point of view is reduce the electrical load from the heat pumps, or eliminate the electrical load from the heat pumps. So, but there's a big question. 55 degrees C is above the temperature where the chemists tell me that we might start doing nasty things to pyrite and changing the composition of the water. So that's where this whole thing is really integrated. We need to understand what temperatures we can safely take this to from a chemical perspective and a structural engineering perspective. I was inspired by Julian's health warning on his talk yesterday. I've put a health warning here. These are photographs of David Walls and David Townsend at the site in Dollar. They're just really nice photographs, and the one with the rainbow makes me happy. This is not our site, but I don't like slides with only words on. So just a bit of context, we are doing the baseline characterisation at the moment. Steph's conducting a detailed search through the local geology and mine history and geometry. Neil, Inside and Steph have already got CCTV camera footage from the Coal Authority and some initial water temperature samples, water chemistry and temperature samples from the shaft that we're wanting to work on. We should be starting our experiments in back end of next year, all the way through to the mid part of the year after. And the idea is to test the effects of different heating and cooling cycles on the water body. We'll monitor the response of the water body with our partner Silixa, who manufacture very sophisticated optical fibres and optical fibre interrogators, and we'll use that to validate the models that Hua Cheng and Jessica are doing. The exact experimental setup is to be decided. We're in the midst of procuring a very experienced contractor, and those negotiations are ongoing. But once we have that contractor in place and we have the agreements with the local landowners, we can proceed. So that's it for now. Thanks for listening, and my cat wants to send you a message to give her low carbon heat to enjoy. She loves our coal stove, and she would really like you to decarbonise her lovely stove experience. Thank you very much.